Okay, so I'm very aware that this is the second to last talk of the session, so I'm going to give you today a brief crash course in tornadoes and why they happen and how they happen in the United Kingdom. Okay, so to start off, this unfortunately isn't in the United Kingdom, but this is me getting excited in front of a storm that's currently trying to produce a tornado in Kansas. So we kind of call this process tornadogenesis. Now, when I'm talking about tornadogenesis, we can split this term into two sections. You've got the tornado section, where a tornado can be defined as a rotating column of air from a cloud base to the surface, and the genesis section, or we call it the origin mode, the formation of these. So, this is a really heavily researched topic in the US, and this is mainly because the US experiences the most tornadoes in anywhere in the world in one location. However, the United Kingdom, it tends to experience more tornadoes per unit area. And this really begs the question of, well, why? If all of this research has been done in the US, why haven't we had a lot done here in the UK? So before I can really go into the stuff that happens in the UK, I'm going to give you an idea of why these tornadoes happen all the way in the States. So here we have something called a supercell thunderstorm. Now, a supercell thunderstorm can be defined as a thunderstorm with a rotating updraft, rather than a standard thunderstorm that you might see in the UK that just kind of rises, rains, and then dissipates. So, in a very kind of standard supercell environment, we tend to experience a lot of this low-level wind shear. So we're talking about higher winds aloft than at the surface. And this brings this vertical rotation, or this overturning of air, right near to the surface. And when this interacts with an updraft, we tend to see this vertical rotation tilted all the way into the horizontal. And this gives us the rotating updraft that we kind of see in these supercell thunderstorms. However, this is very counterintuitive when we think of tornadogenesis. I just told you that this storm needed, well, for a tornado to form, we needed rotation near to the surface, and this lifts rotation away from the surface. So the current ideas are that the downdraft associated with this supercell thunderstorm tilts some of the ambient vertical rotation near to the surface and brings it up into the horizontal and produces our tornado somewhere in this vicinity. So, bringing that kind of idea, the US between these 3 years experienced nearly 4,000 tornadoes, and 80% were from this isolated system, or the supercell thunderstorm. However, when we have a look at the UK, we've experienced significantly less tornadoes, but we also noticed that they're from a different parent storm type. So instead of this nice isolated supercell thunderstorm, we seem to experience most of our tornadoes from this linear system, where a linear system can be defined as a line of thunderstorms often associated with some kind of atmospheric boundary. So here's an idea of what one of these might look like if you're stood in front of one. Now, they look significantly different to the supercell thunderstorm. Often we see a lot of these updrafts going up at the base of this linear system. And it kind of gives the question okay, well, if the supercells produced by rotating, or by bringing vertical rotation into the horizontal, how are these linear systems producing tornadoes? And it really kind of gives us the idea that is it something to do with a similar way that the supercells produce tornadoes, or is it something completely different? So I'm going to now talk about a little bit about what we get in the UK. So this is over here, this is an event from 2007. This is in September, and as you can see, there's a large kind of cold front here that's dissecting the UK in half. Now, if we look at the associated precipitation with this event, we can see this really narrow line of intense precipitation, somewhere in the region of kind of 64 to 96 millimeters per hour, and that's pretty intense in terms of rainfall. And all of these black triangles that are kind of scattered along this line are actually tornado reports from this event. So this event went on and produced 8 tornadoes. However, it's not easy to see why they're producing tornadoes in this kind of manner. Okay, we understand that linear systems produce tornadoes, but why are they producing them? So if you actually have a look a little bit closer, you can see that this line of intense precipitation is split into these regions that are really intense and really quite weak, especially in regards to these two down at the bottom. Now, these gaps are almost an idea of tornadoes, an idea of the kind of pattern that we experience when we see tornadoes. And we call this coring gap. However, this coring gap is very hypothesized at the moment of why they're producing tornadoes. But one of the things that we kind of experience in the precipitation field and also the vorticity field is this coring gap feature. So a lot of these mesoscale boundaries, or the fronts that I've just talked about, I usually have some kind of pre-existing vorticity along with them. So here's a very basic idea. It's just a very kind of two-dimensional aspect of how this happens. Imagine that this black line over here is your frontal systems. This is your cold front moving through, and it's also the vorticity that's associated with this cold front. Now, either side of this front, we've got two different wind directions, maybe varying wind speeds. And as this happens, we get some instability occurring, which breaks up into almost like a wave. So once we get this wave-like form happen, we get areas of divergence and areas of convergence. And eventually, as this wave progresses, it evolves into areas of closed circulations. Now, we call these circulations mesocyclones or mesovortices, and it's usually along these that we find with these gaps in the precipitation. So when we have this gaps in this precipitation, we now have a synonymous area of closed rotation. And this kind of brings me to where I am right now. In the kind of, this is a lot of the backstory of what's happened, and but a lot of the stuff hasn't really been like no one's really dug into it too much. So we're really interested in why these mesocyclones produce these tornadoes. Are they similar to the supercell rotating updrafts that I was talking about, or are they something completely different? So the way I'm looking at this, I'm looking at several events that try and produce 3 or more tornadoes. Now, I've isolated these events because we do have these events in the atmosphere called mesoscale accidents, where a tornado might just spawn out of somewhere that wasn't expected. It's just an accumulation of these ingredients and a tornado is formed. So having 3 or more events kind of verifies that there is something going on, that's a little bit more structural. So I've checked all of these events with the Met Office radar, and this is to get an idea of the fact that they're all now linear systems. So in total, I only found 7 of these events. I actually expected a few more, but so from these 12-year period, I've only got 7 events that produce 3 or more tornadoes from a linear system. Now, one of the interesting things is I started off with my PhD really digging into the details on this, really going deep, really understanding the mesocyclones at their core basis. But then I took a step back and was like, what about the large-scale pattern? What's happening in terms of the synoptic scale? So one thing I noticed instantly is that out of 6 of my cases, you can bin them into 2 separate categories. So I've just very basically called this one type A for now. But type A tends to have a nice kind of cut-off low or some kind of low pressure associated with the synoptic jar and a really nice intense cold front that cuts through the United Kingdom in a north-south orientated manner. Now, these kind of events seem to produce quite a lot of tornadoes. However, we also have this kind of event, where we tend to have a low pressure located over Scandinavia that moves quite slowly to the south and brings in a lot of this northerly cold air. And the front here, instead of being north-south orientated, are east-west orientated. Now this kind of threw me a little bit because I wasn't expecting there to be such an obvious kind of set of bins. I've got one that's very north-south orientated and one that's very east-west orientated. What's the difference? Is there a difference, or are we looking at kind of the same events that are happening just in a different synoptic regime? So this is where I stepped in with the modeling. So unfortunately, due to the lack of data in the UK, especially in terms of velocities and Doppler, we don't have a lot of this. So one of the ways we can understand these events thermodynamically is by using a model. So I'm using the WRF model. And this over here is simulated down to 1 kilometer resolution, and it's the event I showed earlier, the September 2007 event. And as you can see, we've got kind of a very nice output in terms of precipitation, a nice line of intense precipitation that's occurring, and it looks relatively similar. It looks realistic. However, when we start looking at some of these east-west events, we can kind of see that, well, obviously they're weaker to begin with in the first place, but in terms of precipitation, we're not quite resolving it as well as I'd maybe like to. And this, you can still see the structure here, but it's slightly further to the east. We kind of got more of the precipitation rising up to the into Ireland, which isn't existent in terms of the real event. And this kind of really brings me to the point where I was thinking, okay, well, if we've got these events that look very different, and they also seem to go through the simulation very different, and some of them are easy to simulate than others, what's the vorticity looking like? So the vorticity is what I was talking about earlier with the rotational aspect, because this is a really key, what we think it's a really key input, ingredient when talking about tornadogenesis. So in terms of the north-south orientated front, we've got this very nice line of vorticity, which I've kind of talked about before, that breaks up into the waves. And you can see some areas of maxima in here that might be related to these mesocyclones that I was referring to earlier. However, when you look at the vorticity from some of the other east-west orientated cases, it's nowhere near as strong. It's still here, but I chose this to use it on the same scale on purpose to give you an idea that we've got this very strong line of vorticity with some cases, but other cases, absolutely nothing. And this kind of really brings the question, like, A, is this realistic? Are these simulations being simulated properly? And if they are, why do we still see some of these events produce so many tornadoes? Is the vorticity aspect really that important at this scale? Or are we looking at more of like the micro-physical processes going on within the mesocyclones themselves? And this kind of brings me to where I'm at right now. Like, I could have gone into a lot of detail in terms of what I've been doing with the mesocyclones, but I'll just give you a broad overview of like why we're getting these tornadoes and why there's so much of a difference and how many unknowns there are. But yeah, thank you very much, and I'll take some questions.